Hi, welcome back. We're going to talk today about the last section of our acid-base notes, which covers weak acid-base pH calculations. And then we're going to learn a little bit about redox reactions. So that'll round out our entire types of reactions section, which covers acid-base reactions, which we've called neutralization reactions, precipitation reactions, that goes back to our net ionic equations and using solubility rules. And then finally, what we're going to learn in this lesson, redox reactions. Okay, so let's get into the last section of acid and base, which is going to cover how to calculate the pH of a weak acid or base. And remember, for weak acid or base, they're not going to have complete dissociation, all right? So they won't completely separate into ions, and so we set up an equilibrium reaction where we can have one side favored over the other. And in our case, that means that some of the original acid is going to remain in solution, and then we're also going to create some hydronium ions in solution as well. And remember that pH is equal to the negative log of the hydronium ion concentration. So even though in this problem it says that we have a concentration of acetic acid that's equal to 0.3 molar, that doesn't mean that we're going to have 0.3 molar concentration of hydronium ions, because some of the acid itself is going to remain. So while some of this 0.3 molar concentration is going to decrease for the acetic acid, while the hydronium ion concentration increases, it's not all going to get used up. So we have to figure out what concentration the hydronium ion is going to be, and then plug that into our negative log formula. Now, typically in an AP chemistry, you'll go through how to actually make that calculation using what's called an ICE table, or sometimes they call it a RICE table, where the R stands for the reaction, and that's this top line up here where we actually have the reactant, and then you have the products over here. But I don't like calling it a RICE table. For whatever reason, I just like ICE table. So that's the nomenclature I use in my notes. We're not going to go through how to actually use the ICE table in pre-AP chemistry. I'll save that for AP Chem. What we do want to talk about, at least for the purposes of our notes here today, is that we're going to say that a weak acid is going to be symbolized by HA, okay? And that's just for right now while I'm talking about it in this discussion. Of course, an actual reaction is going to have a real acid that they'll be referring to, but just for me, for right now, I'm going to refer to it as HA. We want to write what's called our equilibrium expression, and that's what we have here, where it says Ka equals, okay? Now, the Ka is going to be the acid dissociation constant, and that's particular to any given acid, whether it's acetic acid in this case or maybe carbonic acid in a different case. Nevertheless, each acid is going to have its own Ka value, and that will be given to you in the problem. All right, so what I have here is the expression for this problem's acid, and I'm just going to generalize that using that HA that we talked about a second ago. So we're going to say that the acid equilibrium constant is going to be equal to x squared over the concentration of the weak acid, okay? X squared over the concentration of the weak acid. Pardon my really bad handwriting there. Okay, so just to confirm that you understand, the Ka is going to be given to you in the problem, and the concentration of the weak acid will be given to you in the problem. And what you're looking for is X, okay? X is the thing that you want to know, and X is going to stand for the concentration of the hydronium ion. Okay, X is the concentration of the hydronium ion. And remember that this is what you're going to plug into the negative log formula in order to figure out what the pH is. Okay, so now that we have that, let's go through and try and work the problem. Okay, so the original problem up here says determine the pH of 0.3 molar acetic acid with a Ka value of 1.8 times 10 to the negative fifth. So that's what we're going to do. We are going to figure out what that concentration is first for the hydronium ion, and then we're going to plug that into our negative log equation. So we're just going to plug into that formula that we had a second ago. So we've got 1.8 times 10 to the negative fifth. This is the Ka value. That is equal to x squared, and we want to know what x is, over the concentration of the acid, which that was 0.30 molar. Okay, so obviously we're going to multiply both sides by the 0.3 molar. And then since we want to know what x is and not x squared, we'll take the square root of both sides. Okay, so we'll say x is equal to, normally, of course, when you take the square root, it's going to be plus or minus, but since you can't have a negative concentration of something, it's just going to be the positive of this. So we're going to say the square root of 0.30 molar times 1.8 times 10 to the negative fifth. Usually, you know that I'm a stickler for units, and I would typically definitely have a unit for that Ka value. But units for Ka and Kb, the base constant values, they actually change depending on what kind of reaction we have. There's things called orders of reaction, and based on what those are, the units of K can actually change. So in this case, I'm not going to go into that, and I'm just going to leave it blank. Since we know that X stands for the concentration of the hydronium ion, suffice it to say that molarity will be the unit that we end up with in the end of this problem, since we're solving for a concentration. All right, so that's what we're going to type into our calculator. So I have my calculator with me here at the house. You can use one online, or you can use your own calculator at home, whether it be graphing or scientific. So the first thing that we need to remember is that when you're typing in scientific notation, please put that in parentheses, no matter what kind of calculator you happen to be using. So I've got 1.8 times 10 to the negative fifth in parentheses, and I'm going to multiply that by 0.3, and then take the square root of that answer. And when I do that, I am getting 0.00232, and I'm going to put a capital M for molar there. So that is the concentration of the hydronium ion. Okay, that is not the final answer to this problem. Okay, what we need to do now is take this number and plug it into our negative log equation. Okay, so I'm going to take that, I'm going to plug that into my negative log formula. So I've got negative log of that number. Now remember, when you plug this into your calculator, use the big long number. Don't use just the 0.232 number that I have here. Use everything the calculator gives you. So I type that in, and I am ending up with a pH value that is equal to 2.63. Okay, I've got a pH value of 2.63. Now, if you forgot that acetic acid was a weak acid and not a strong acid, then you incorrectly would have tried to put the negative log of the original acid concentration into your calculator. So you would have said negative log of the 0.3 value. And if you had done the negative log of the 0.3 molar acetic acid, then you would have gotten a pH of 0.523. And that would have been what you said was the answer to this question, when the real answer is 2.63. Okay, so you'd be a far cry off from what the actual correct answer is on a homework quiz or test. So make sure that you're still paying attention to your strong acid rules. Remember that it's hydrochloric, hydrobromic, and hydroiodoic are strong acids, in addition to any acids that have 2 or more oxygens than they have hydrogens. Okay, if you have an organic acid, okay, so in other words, an acid that's got carbon in it, then that's a weak acid. Or if it doesn't fit the rules that I just mentioned, that's a weak acid, and you would need to go through the process that I just talked about, where you would have the Ka value once again equal to x squared over the concentration of the weak acid that they give you in the problem. Okay, you're going to solve for x, and then you're going to plug x into the negative log formula. So you have negative log base 10, and then you would put x in here, and that's going to give you your correct pH value. Okay, so that covers your acid-base notes through all of the calculations for strong and weak acids and bases, as well as the types of acids and bases, Arrhenius and Bronsted-Lowry. Now, let's move into our notes on oxidation reduction. All right, so for oxidation reduction reactions, these are kind of like the leftover reactions. You should be able to identify that a reaction is an acid-base reaction by looking for an acid, anything that starts with hydrogen, and looking for a base, something that has OH in it. And that you would get a water and salt as your products, because that's a neutralization reaction. So that's how you recognize that. And then our precipitation reactions, obviously they're going to be double displacement reactions, because they have to be aqueous in order for ions to interact with each other and possibly give us a precipitant or a solid. So you would look for a double displacement reaction to decide whether or not something is going to be precipitation. And then to decide if something's going to be a redox reaction, well, that's just the leftovers, okay? If it's not acid-base and it's not precipitation, it has to be redox. So those are the three main types of reactions that exist, and everything needs to fit into one of those three categories. All right, so a redox reaction is going to track the flow of electrons between chemical species in a reaction, and we need to be able to do that. And we're going to use a little mnemonic device here. I have two of them. They both accomplish the same thing, and you just decide which one you like the best, okay? So you can use oil rig as your mnemonic device, where oxidation is loss, reduction is gain. In this one, you just have to remember that we're talking about electrons. So if you lose electrons from an element, then it's oxidation, it's oxidized, and if you gain electrons, then it was reduced. Or you can use Leo goes Gur, okay? We're talking about Leo the lion. So Leo, lose electrons, oxidize, and Gur, gain electrons, reduce. I like this one better because I don't have to remember that I'm talking about electrons. Since it's part of the mnemonic, there's no chance of me messing it up. Okay, so let's talk about how we're going to do this. If we're going to be able to track the flow of electrons, then we have to remember how to calculate the oxidation state of a particular element within a compound. We did this back when we did predicting reactions earlier in the year, and it was mainly for deciding If you had a non-metallic oxide plus water, you would get an acid in a synthesis reaction. Or if you had the reverse of that, a decomposition of an acid to create a non-metallic oxide. The problem was we were trying to figure out what non-metallic oxide would I be creating, or what acid would I be creating depending on the non-metallic oxide that I used. So that, of course, is the example that I have here. What's the charge of sulfur in this sulfuric acid? So we want to know particularly what this oxidation state is. If you look at your periodic table for sulfur, you'll see that it has a bunch of those little numbers in there that stands for the oxidation states. And we know that sulfur could be, based off of our periodic table, it could be a 2, a 4, or a 6. So we need to figure out exactly which version of this sulfur we have. Remember, all elements and compounds are neutral, which means that they have a 0 charge. So if, for example, we have just the element sodium, okay, just the element sodium. Since it's an element by itself, that has a neutral or 0 charge, okay? Here we have H2SO4, sulfuric acid. Since that's a compound, that has a neutral charge. So overall, sulfuric acid has 0 charge. That means the charge of hydrogen, sulfur, and oxygen all have to add up to equal 0. And so we're going to use that to our aid here to figure out what sulfur is. So, okay, we've got 2 hydrogens, and we know that each hydrogen has to have a +1 oxidation state. Hydrogen can't have a different oxidation state. It can only be +1. We don't know what the oxidation state of sulfur is, but we know that we only have 1 of them. And then we know that we have 4 oxygens, and oxygen can only be a -2 charge. And then all of that has to add up to be 0. All right, so 4 times -2 gives me -8, and 2 times +1 gives me +2. And -8 plus 2 gives me -6. Move that to the other side of the equal sign, and that means that this sulfur has to be a +6 charge, okay? Being able to do that will allow me to track what happens to a particular element from one side of the reaction arrow to the other side of the reaction arrow during a redox reaction. So let's take a look at this example right here. Okay, so we have zinc plus cupric sulfate, and then that's going to give us zinc 2 sulfate plus copper. All right, well, obviously, since that's just zinc, that means that it has a 0 charge all on its own, because all elements and compounds are neutrally charged. And then this copper over here, that's all by itself, so it's got a 0 charge as well. Well, now we want to figure out what happened, or what kind of copper do we have here, and what kind of zinc do we have here. We actually don't have to go through all the calculation we did just a second ago with the sulfuric acid. We can take a shortcut. We should, I hope, remember that from our 2323s earlier in the year when we did nomenclature, that copper could be a 1 or it could be a 2, okay? And zinc can only be a 2 when it's an ion, okay? So zinc can only be a 2. That is a terrible 2. And because zinc can only be a 2, we know for a fact that one's +2 charge. It also should make sense because it's partnered up with a SO, and remember, SOs, COs, and CROs are -2. So that cancels out well. But for that same reason, this copper over here, it has to be the +2 version of copper because it's partnered with a SO, CO, or CRO. And there's no number subscript on the copper. If this was the +1 version of copper, then we should have a 2 down here that we would have crisscrossed down from the sulfate, and it's not there. That means that the +2 of copper canceled out with the -2 for the sulfate group, so we have the +2 version of copper. All right, with that being said, we can say, okay, the zinc metal went from 0 to a +2 charge, and the copper ion that was +2 became just copper metal with a 0 charge. Now we can use our mnemonic device from earlier, and I like to use Leo goes Gur, okay? So Leo goes Gur. All right, so if you lose electrons, you are oxidized. Remember, electrons are negative, so if you lose them, then you become positively charged. And that's this first situation up here, okay? We went from a 0 charge to a +2 charge. The only way that we could have done that is if we lost 2 electrons. So that means that zinc was oxidized in this problem, or in that reaction, okay? The zinc was oxidized. And then down here, the copper went from a +2 charge to a 0 charge, which means that it had to gain 2 electrons to cancel out those 2 positive charges. So that means that the copper here, the copper ions, were reduced to copper metal. And that's it for redox reactions. You have to be able to track the charges from one side of the reaction arrow to the other, and then use your mnemonic device to figure out which element was oxidized and which element was reduced. All right, so I'd like to do a few more examples of redox reactions with you just to make sure that you absolutely know what's going on. So in this problem, letter A, we have chromium with a +1 charge on the left-hand side of the reaction arrow. And then on the right-hand side of the reaction arrow, you can see that it has a +3 charge. So we're trying to determine what happened to chromium from the left-hand side to the right-hand side of the reaction arrow. So I usually just do these little brackets, like, lines or whatever. So we went from a +1 to a +3. What had to happen there in order to get more positive? We had to have lost additional electrons. So lose electrons, Leo, lose electrons, oxidized. So that means in this case, the chromium was oxidized. Now, of course, that automatically means that the 10 was reduced, but let's go through the motions and see if we can understand why. So we went from a +4 to a +2. That means we got less positive. In order to get less positive, you have to gain some negatives, and electrons are negative. So we gain electrons, and that means reduced, the Gur part of our mnemonic device. So the 10 was reduced and the chromium was oxidized. All right, let's look at letter B here. So we have mercury 2+, okay? And then over here, we just have mercury, the metal, the element. Remember I told y'all that mercury was a diatomic molecule. And so that's why it's written down here Hg2. So it's just diatomic. But this is the metal mercury. So what do we know about all elements and compounds? We know that they're neutral, they're 0 charge. So we can say then that this mercury right here has a 0 charge. And we can say that the iron over here on the left-hand side, that has a 0 charge. That looks like a 6 to me, so I'm going to rewrite that real quick. Okay, so now let's track everything. So we're going to look at the mercury. We're going to go from this side to this side. So it went from a +2 charge to a 0 charge. That means it became less positive, which means it had to gain electrons. So gain electrons, reduce for Gur. Okay, and then that means that the iron, okay, it went from a 0 charge to +3. It became more positive. That means it lost electrons. Lose electrons means oxidized. Okay, all right, so this last one here, I'm gonna let y'all have a few seconds to try and figure that one out on your own, and then we'll come back and see how you did. Okay, so on the left-hand side, arsenic has a 0 charge because it's just the element arsenic, and we know that all elements and compounds are neutral, so that's a 0. And then chlorine, we have the diatomic molecule Cl2. That's a neutral charge as well because it's just the molecule. So chlorine, 0 charge. Okay, now when looking at the product side, we've got AsCl3, right? Now, there's a 3 on the chlorine as a subscript, and we know that that came from crisscross reducing. That means that 3 had to come from the arsenic. So this arsenic has to be a +3 arsenic, okay? And the chlorine, of course, that means it has to be the -1 version of chlorine because there's 3 of them. So if you have 3 chlorines with a -1 charge each, and you have 1 arsenic with a +3 charge, then they cancel each other out and are neutral, which remember, all elements and compounds have to be neutral. Okay, so when we write it out, that means that we went from a neutral arsenic on the left to a +3 version of arsenic on the right. And we went from neutral chlorine on the left to -1 chlorine ions on the right. So now we can identify what happened across the arrow. So for the arsenic, we got more positive. That means we lost electrons. So that's Leo, lose electrons, oxidized. So the arsenic was oxidized, which means that the chlorine had to be reduced. So we got more negative. We went from 0 to a -1 charge. So that means we gained electrons. So reduction or gain electrons reduced. Okay. So hopefully that's what you came up with when you tried this problem out yourself. So you should now be able to identify what's an acid-base reaction, what is a precipitation reaction, and what is a redox reaction, and can you identify what was oxidized, what was reduced, and can you track the flow of electrons from one side of the reaction arrow to the other. I hope that all of this helped and was beneficial, and that is the last section of notes that's going to be covered on the test. So you should know everything from properties of water, which was at the beginning of our notes packet, all the way through these redox reactions for this test. If you have any questions, please don't hesitate to reach out or join one of our tutorial sessions that we have for you guys on Monday, Wednesday, and Friday. Thanks for learning with me. Bye.